Ever pick up a pebble and find yourself wondering what it's made of? Like if you zoom in closer and closer, what are the fundamental building blocks of, well, everything? Today, we're on a deep dive into a mind-bending idea called close-packed singularity geometry, where the answer might just be tiny, perfectly packed spheres.
It's a wild concept, right?
Yeah.
We're talking about the work of physicist and mathematician Nick Treff, who suggests that if we reimagine the very points in space as these infinitesimal spheres, it could revolutionize our understanding of, well, reality itself.
Okay, let's unpack this. So instead of points being nothing, they're actually these tiny, tiny spheres. Is it like imagining pixels on a screen, but in 3D?
That's a great analogy. Now, you might think, okay, but how does that change anything? Aren't we just swapping out one abstract concept for another? But here's where it gets interesting. You see, if we think about points as having some structure, even at the smallest possible scale, then the relationships between those points become incredibly important.
So it's not just about the spheres themselves, but how they interact, how they fit together.
Exactly. Think about it this way. Even though an ant is tiny, its relationship to the colony, its role in the bigger picture, is still vital. It's the same with these spheres. They might be infinitesimal, but their interactions could be the key to understanding the structure of the universe.
That's already bending my mind a bit. So how do these spheres actually arrange themselves?
Well, the universe seems to have a preference for efficiency, and these spheres are no different. They naturally arrange themselves in the most stable, dense configurations possible.
Kind of like when you see oranges stacked perfectly at the grocery store, there's a specific way they fit together to make the most of the space.
Precisely. And just like those oranges, there are specific arrangements of spheres that are more stable and efficient than others. These arrangements form what we call lattices.
All right, so we've gone from points to spheres, and now we've got lattices. What kind of lattices are we talking about? Is this where it gets super complicated?
Not at all. In fact, some of the most efficient lattices are also the most familiar. We're talking about patterns you've probably seen countless times before, a simple checkerboard pattern, or even the hexagonal structure of a honeycomb.
Checkerboards, honeycombs, those are E-patterns I've seen before. But we're talking about them being made out of tiny, invisible spheres. It's like there's a hidden code in these everyday patterns, right?
Absolutely. What's remarkable is that these simple arrangements, dictated by the geometry of the spheres, can actually give rise to incredibly complex and organized structures. Just like a few lines of code can create a complex program, these simple lattices are the foundation for something much bigger.
So how do we get from these checkerboard and honeycomb lattices to, well, something more than just a flat pattern? How do we get to 3 dimensions?
That's where things get really interesting. Imagine stacking those lattices on top of each other, layer by layer. The way those layers interact, the way the spheres nestle into the spaces between each other. That's where the real magic happens.
So by packing these spheres together, we're not just creating patterns, we're creating shapes.
Exactly. And not just any shapes. Trey shows how these close-packed spheres naturally give rise to some of the most fundamental and symmetrical shapes in geometry. The Platonic solids.
Wait, platonic solids? Like
Yeah.
those perfectly symmetrical shapes you might remember from geometry class? The cube, the tetrahedron, those guys?
Precisely. For centuries, people have ascribed almost mystical significance to these shapes. But what Triff is suggesting is that they're not inherently special in some metaphysical sense. Instead, they emerge naturally from the simple act of packing spheres as efficiently as possible.
It's like the universe is playing 3D Tetris, and those platonic solids are the winning combinations.
I love that analogy. It really captures the elegance of this idea, and it gets even more interesting when we get to the icosahedron.
The 20-sided one, right? What's so special about the icosahedron?
The icosahedron is fascinating because it emerges from a more intricate arrangement of the spheres, one that reveals deeper connections between the different types of lattices. It's not just a simple stacking of squares or hexagons anymore. It's a complex interplay of different patterns all working together to create this highly symmetrical shape.
Now, this is where I had to really wrap my head around what Trafe was saying, but stick with me because it's pretty amazing. It's like within this packing of spheres, you suddenly have this incredibly complex 20-sided shape appear out of nowhere.
It's a bit of a eureka moment. And it hints at something profound. We often focus on what we can easily see and measure. But the icosahedron reminds us that there might be layers of complexity hidden within seemingly simple structures.
So we've gone from points to spheres, from lattices to frickin' platonic solids. This close-packed singularity is already blowing my mind. Where does Triff go from here?
Well, up until now, we've been focusing on the spheres themselves and the shapes they create. But what about the spaces between those spheres? What about the surfaces that connect them? That's where things get really interesting, and where we can find an unexpected connection to something we experience every day. Soap bubbles.
Okay, you're going to have to connect these dots for me. We've got these packed spheres, these platonic solids. How does that lead us to soup bubbles?
Well, think about the surfaces that form between the spheres in this close packed structure. You've got the surfaces defined by the square lattice, the hexagonal lattice, and even some more complex ones from the icosahedron.
Right, those intricate non-repeating patterns we talked about.
Exactly. Now imagine dipping those packed spheres into soaky water. What do you think would happen?
I'm picturing a bunch of tiny bubble-covered spheres, like a microscopic foam party.
Not quite, but you're on the right track. Soap films are fascinating because they naturally try to minimize their surface area. It turns out that the spaces between close-packed spheres create the perfect conditions for these minimum surfaces to form.
So the soap film is stretching across the gaps between the spheres, trying to use as little film as possible.
Precisely. And that's where the connection to our packed spheres becomes really clear. Remember when we talked about the rhombic dodecahedron, that 12-sided shape with diamond-shaped faces?
Yeah, it looks like a really complex die.
Well, it turns out that the angles between the faces of a rhombic dodecahedron are exactly the angles that soap films form when they meet.
Wait, seriously? So those perfectly spaced bubbles, those mesmerizing patterns we see in soap films, they're not just random, they're dictated by this close-packed geometry.
It's a pretty amazing example of how nature, in its pursuit of efficiency, often arrives at the same solutions we observe in mathematics. Over a century ago, physicist Joseph Plateau outlined 3 laws that govern the behavior of soap films. One of those laws states that when 3 soap films meet, they always form an angle of 120 degrees, and guess what? That's the same angle we find between the faces of the rhombic dodecahedron.
So we've got this hidden code in the way spheres pack together, a code that determines the shapes of bubbles and maybe even, as Triff suggests, the very structure of the universe itself.
And it gets even more interesting. Triff's work suggests that this close-packed model might even challenge some of those established laws of physics, like Plateau's laws, or at least provide a new way to understand them.
So it's not about throwing out the old rule book. It's about finding a deeper level of understanding, a new perspective on the rules themselves.
Exactly. If space itself is structured according to these close-packed principles, it changes how we interpret everything, from the behavior of matter to the very nature of reality.
So if we can crack the code of close-packed singularity, who knows what we might discover.
It's a tantalizing thought, isn't it?
It really is. This deep dive has been a wild ride through the geometry of the universe. From tiny spheres to platonic solids to the surprising connection with soap bubbles, it seems like we've only just scratched the surface of what close-packed singularity might reveal about the fabric of reality. Until next time, keep looking for those hidden connections. You never know what you might find.